Good morning, everybody. This is Prajwal from Artificial Intelligence and Robotics Lab, and I will present our recent work, DeepMAO, a multiscale aware overcomplete network for building segmentation in satellite imagery. Humans have been expressing creativity in architecture for centuries. Each building in a dense urban environment is likely to have varied sizes and complex shaped geometrical footprints. And through various remote sensing methods such as satellite electro-optical imagery and synthetic aperture radar systems, we are able to observe these complex building footprints. Remote sensing has more prominent applications such as disaster response in case of floods, earthquakes, and change monitoring for forest and urban cover. A data-driven machine learning approach to monitor urban buildings, where the size and shape of each building is taken into account, is through semantic segmentation with deep neural networks. Semantic segmentation, which is pixel-wise classification of a dense cluttered environment, has proven to be a challenge given the diversity in the strength of the signals provided to neural networks. Deep learning techniques tend to generalize to buildings with high pixel numbers. Here we can see a small crop of an input image, ground truth labels, and their corresponding unit predictions. This trained model of unit can predict medium-sized buildings down to the pixel fairly well, but misses out on buildings with smaller footprints due to their low pixel representation. Small building segmentation is rendered a challenge in such a situation. And I say medium-sized buildings because there are much larger buildings in a full-size remote sensing image. This is a picture from the SpaceNet 6 challenge dataset, our primary dataset for this paper. And here is the ground truth label. Tiling of such an image can only go so far before semantic context of large buildings is lost. Feature extraction in convolutional neural networks happen through multiple layers. In an encoder, low-level features are captured in the initial layers, and as the layers get deeper, the receptive field increases, making the last layer focus on high-level semantic features. Layer 3's receptive field is denoted by the color yellow, whereas the receptive field of layer 2 is denoted by the green color. Layer 3 has a higher receptive field than layer 2. In a unit, this encoder structure is then followed by a decoder, and this has been the norm for many such semantic segmentation models. On the flip side, to solve the problem of missing small buildings, we look to decrease the receptive field deeper through the layers. This is possible through overcomplete architectures, relatively underexplored method for semantic segmentation. Overcomplete architectures basically constitute of layers in a network that have more neurons than the previous layer. These architectures have been historically proposed to work in the presence of noise. In a convolutional network, it would look like this, where layer 3 has a smaller receptive field than layer 2. This is an architecture proposed recently, wherein an input is separately passed to an overcomplete branch and an undercomplete branch that concatenate and provide a prediction. The authors focus on segmenting small features more accurately in an already small medical image. The same cannot be directly applied to remote sensing due to the size of the images that are input to the network. Overcompleteness also has harsh memory penalties followed by magnitude slower training time and inference time. Hence, we propose DeepMAO, a network that is aware of both small and big buildings when performing semantic segmentation. It consists of an undercomplete unit and an overcomplete branch. The overcomplete branch takes the output of the first layer of the undercomplete branch. This layer is passed through subsequently larger layers in a spatial sense through bilinear upsampling. The output of the OC branch is then added to the output of the last decoded layer and passed through a segmentation head. From the GradCam visualizations above, we can see that as the receptive field decreases through the layers, the model focuses on small features and is supplementary to the main unit. This modification adds about 1% of the parameters of the original unit and is comparable in terms of memory usage and training time. Our training loss L-seg is a combination of dice loss and focal loss that is computed on the final prediction of the network with its corresponding pixel-wise ground truth labels. To increase the pixel representation of smaller buildings in the dataset, we introduce a novel augmentation scheme called loss mix that is self-regulative in nature. We tile the training pairs into a number of patches and compute the L1 loss for each, and pick the patch with the highest loss for augmentation. This learning scheme is introduced after the model has been trained well enough to segment larger buildings, and so the assumption is that we pick patches where More often than not, there are small buildings that are being missed, and hence increase the instances of harder samples. Another visualization of the layers of the encoder of the UNet and OC branches, where UNet shifts focus from low-level features to global features. The OC branch, due to its decreasing receptive field, focuses on low-level features, which is basically small buildings and integrated geometries in larger buildings. For this work, we have used three aerial imaging datasets, namely the SpaceNet 6 Electro-Optical dataset, along with its Synthetic Aperture Radar counterpart, and the INRIA aerial imaging labeling dataset. Here are the results of different models on the SpaceNet 6 dataset. We have provided the F1 scores of varying building size brackets. The first column is for the smallest of buildings of footprint size 10 to 56 meters squared, medium to larger buildings of size greater than 56 meters squared, and an overall F1 score with all building sizes considered. DeepMAO outperforms all the models in all building size brackets with an increase of 4.5% for small buildings and an increase of 2.5% in the overall F1 score. In the speckle-ridden SAR modality, we observed an increase in the overall F1 score of 1%. We also have an increase of around 1% in the intersection over union scores for the INRIA aerial imaging dataset. This is a graph of performance over various building sizes. Due to DeepMAO's nature of focusing on small buildings and integrated geometric footprints of larger buildings, a bump in F1 score is observed in the smallest and largest building footprint sizes. Here is an example of segmentation predictions of UNet and DeepMAO, where smaller buildings are successfully segmented. Here is an ablation study table where it is observed that loss mix augmentation scheme is beneficial to the other state-of-the-art models. But due to DeepMAO's capability to focus on small buildings, it is able to make the most of loss mix and evidently has the largest relative increase in F1 scores. Here are some selective crops of segmentation of the SAR modality where DeepMAO is able to outperform UNet. Here are a few more examples of DeepMAO segmenting smaller buildings in the SpaceNet 6 and the INRIA dataset. In conclusion, this is the first work to focus on small building segmentation where we propose a novel architecture which consists of an overcomplete branch tasked to focus on small and integrate building footprints. We propose a novel self-regulative learning scheme termed loss mix where the hardest to segment patches are used as an augmentation. We have achieved a 2.5% and a 1% increase in overall segmentation performance of EO and SAR modalities. We have also achieved a 4% increase in small building segmentation. Thank you.